All right, you guys, question 37 didn't come out very well when I scanned it in, but listen and I'll try to type it out over here on the edge when we get to the appropriate spaces. But we're looking, it's a volume problem, and it gives us what we're looking for. Let me read it out loud really quick. You can also look on page 161. Water is stored in a conical tank with a faucet at the bottom. The tank has a depth of 24 inches and a radius of 9 inches. And as you can see, I drew it here. Here's my depth, 24 inches. And my bottom has a radius of 9 inches. And I think maybe they were thinking it was a little bit different. I drew it this way. I was trying to decide if they thought that it was the other way. But anyway, that's the way I drew it. If the faucet is open to allow the water to flow at a rate of 5 cubic inches per second, what will the depth of the water be after 2 minutes? So I wrote everything out from my DeSaya, right? Here's my volume formula with R of a conic, of the conic cylinder. 1/3 pi r squared times h. We have a radius and we have height. And it gave us both of those things, right? It gave us both the radius, which was 9, and the height, which is 24. So I simply put those two numbers into the formula and solved. So my volume to start was approximately 2,035.75 cubic inches. Okay, and then under here for the rest of my DeSaya, I have my rate of drainage is 5 cubic inches per second. But you have to be careful with the end of this problem. This is where it's going to get confusing. So I'm going to tell you right now. Let me see if I can type it over here because you can't really see it very well. So what happens as we're draining water out of this conic section is that the radius and the height are changing. Either the height's changing and the radius is changing, and it's changing how much volume you're going to have. And we just need to find that rate of change. So we know the original ratio of the radius to the height is 9 to 24. So I'm just going to reduce that to 3/8 of the height. Okay, so the radius is 3/8 of the height, and this is going to become very important when we get farther into the problem. The first part, though, we don't have to. So I did DeSaya again. Here, I said y, because I know if I have this rate of change that it's going to be a linear process. So I said y is going to be my volume, my cubic inches in the tank, and I said x is going to be seconds, because it's cubic inches per second. So then I just created my model here, my equation. Y equals my original volume, 2035.75 minus 5 times x, right? And then I put the amount of seconds that are in 2 minutes, because it's asking me to find the volume after 2 minutes. But it's asking me to find the volume that's left in 2 minutes. Hold on, let me read it here really quick. Well, the depth, it's actually asking me to find the height after 2 minutes. So the first thing I had to do, though, was to find the volume after 2 minutes. I went and did that, and this is what I got, approximately 1,435.75. Then I put that back in where my volume was in the original equation, and that's this one here. Okay, and you can't see it very well, and I'm kind of in a hurry here, so I'm just going to read it off to you. Well, maybe I can type it up really quick on this side over here. What this says is 1,435.75 cubic inches is equal to, so my original formula was, right, 1/3 times pi times the radius squared, but that's where I'm going to use this 3/8 of the height. So I'm going to put 3/8 times the height, and that quantity squared, okay, times the original height right there. Okay, so I have to enter in all of those things. And then when I solve for this, what I get, and you have to take this h squared here and this other h here that's going to give you a cubic h that you're going to have to take the cubed root of at the end, but you're going to get approximately 21.36 inches depth after 2 minutes.